We've arrived. End of the line. Boss fight. You can like hear the music change. It's getting like really tense. Levenstein's monster coming up. Say monster? Definitely meant to say algorithm. 100% meant to say algorithm. My fault. You get excited. So, my plan for this video is I want to talk a little bit about how Levenstein's algorithm is supposed to work. Um, and then a little bit more about like how you're going to have to sort of like work the definitions like to get them in a form that Coq is willing to accept. Up at the top of the file, I gave a link to the Wikipedia article on Levenstein at a distance, and I think it's a great read. It's going to give you a totally different perspective on how this algorithm works, talking about a matrix and so on. And that matrix is actually the efficient way to implement it. Like, let's not worry about that here. We don't know how to do matrices in Coq or whatever. We're taking a very different approach. It's an approach that's going to later let us prove things about our algorithm, which is pretty cool. And it's harder to prove things about the matrix form. But in any case, we're just going to do it slightly differently. I still think it's really worthwhile to get that other perspective because I think that'll add a lot of clarity. Okay, so let's see how to define this function. How's it going to work? Well, here's the type. We give it to you. You take in a source and target strand, and you should produce a list of edits that really ought to be valid, going from source to target, and then it also ought to be minimal. How are we going to do that? Well, the secret is we're going to write an optimization algorithm. What we're going to do is, at every juncture we can, we're going to look and we're going to say, what are our possible edits? Let's choose the minimal option. Right? And by choosing the minimum at every circumstance, it turns out in this case, that'll guarantee that we get the minimum in general. Not true for every algorithm, but definitely true here. Great, let's take a look. So here's the key idea. You look at what the possibilities are and you choose the cheapest one. Just a quick aside, I'm not going to talk in this description at all about what to do if source or target is empty. If you have no source strand and you want to generate some given target strand, what could you do but generate add edits? And if you have a source strand but no target strand, what could you do but generate delete edits? There's nothing else to be done. If they're both empty, maybe you don't need to do any edits at all. So those, I think, are sort of the easy cases, though easy is maybe a word I wouldn't apply to this function. The most interesting or complex case is the one when source is equal to b1 source prime or b1 source or whatever, and target is equal to b2 target. Okay, here's the idea. First, we can choose, okay, if b1 and b2 are the same, then you could do a copy, right? That's almost certainly the right choice, but we don't know. We'll just say, well, that's one way to go. If b1 and b2 are different, you could do a substitute and then continue on having knocked a base off of both source and target. There are other options. You could delete b1 and then continue on with source and leave b2 on the front of target. Okay, or you could add base 2, the base that we need to have in our output target, and continue on leaving the source strand alone with b1 still on it and target has shrunk. So argument 3 is a function that we defined a while back. Maybe go take a look at it. I think it's in maybe day 3 recursion. I'm not sure. Maybe it's in day 2. Take a look at it. It's a useful function here. You might say, but Prof. Greenberg, there's 4 cases. Why are you talking about argument 3? So in our code, these are implemented in sort of the same case, right? We just sort of decide between copy and substitute by looking at b1 and b2. And you'll know exactly what I'm talking about if you've done subedit already. Okay, so that's the general idea, right? This will be one case, this will be another case, and this will be another case of your argument 3 that you'll need to choose the best one of. And then you'll talk about total cost and so on. Now, we here want to talk about the cost of this edit is the same as the cost of this edit, is the same as the cost of this edit, and this one is free. But you'll notice after the fact, these 2 edits, these continue on with both just source and target. We've removed a base from both strands. This one, we continue on with source, but target stays the same, so we've only removed a base from our source strand. And then for this last one, we leave the source strand alone and we only remove a base from target. So each of these will have different follow-up edits that will be possible. So when you talk about argument 3 considering cost, you'll have to look at the total cost of all of the edits that will result of these choices that have been made. That's what you'll have to do. Okay, one last thing. Let's talk about how you're going to get this function defined in Coq. Well, what are you going to do? It's going to be recursive on both of these, but then look, in these 2 cases, source and target both decrease, right? In both cases, we take a base off of both. In this case, source decreases, but target doesn't. And in this case, source target decreases, but source stays the same. Okay, there's no uniformly decreasing argument. There's no argument that decreases on every recursion. What are we going to do? Well, you're going to need to use the inner loop let fix trick we use to define merge. So what's your definition going to look like? What's it going to look like? Let's give you the right skeleton. Right? It's going to look something like match source target with, and then you'll have a bunch of cases, but the interesting case is this one. Let me rename these just source and target just because that's the name that I used up here. Right. Now in here, you'll say like, you'll do something that gets you the separate copy edits. And then you'll do, right, underscore CU. There we go. Then you'll do delete edits. And then you'll do add edits. And then you'll do something with argument 3. Right, and each of these underscores will contain some recursive call. So really you'll need to do something like this, like let fix inner, and then something like that merge trick. So like inner target equals in. Right? Your function is going to look something broadly like this. Right? Well, there's a bunch of other stuff that needs to get filled in here. You need some other matches. You need to figure out what goes here. You need to figure out what goes here. But this is the gist. There's a lot going on. To get this function defined and working correctly, you're going to have to not only understand this explanation of the algorithm, you're going to have to understand how to use argument 3, you're going to have to understand how cost works, and you're going to have to understand this let fix trick. So it's a real synthesis. It's a bunch of different things. I recommend figure out what goes in each of these cases first. Right? And then try to write the function the way you want. Like it won't work. Like you'll have to put a fail in front of it or something, right? Like at first your implementation of it isn't going to be the right thing. But then once you've sort of got some confidence, like, okay, the code looks right even if Coq doesn't accept it, then apply the let fix inner trick to use the inner loop for the bits that you need the inner loop for. And that should let you get a decreasing function the same way we got one for merge and you had one for subset for the ordered lists. Hopefully this makes sense. I expect almost everyone is going to have questions about this. So let's do public topics on Zulip because lots of people are going to have questions. And if possible, let's try to have public discussions without sharing concrete bits of code. If you do need to share code, maybe either send it to me as a private message and we'll work out some sort of schematic thing, or we'll find ways to share just parts of the code for things that you're stuck on. I'd love it if people could spend some time on their own grappling with writing this function in the right way. I think it's a good experience to sort of like invest a bit of energy here and sort of like, what does it take to sort of fight against the type checker, or I prefer to think cooperate with the type checker to get a program that terminates and sort of ticks all of the boxes. Okay. This function is a challenge, but I think you're all up to it. You've got all of the skills. You've got all of the knowledge that you need to get here. It's just going to take a little bit of work. I look forward to helping you figure it out, and I hope this is a fun day. Cheers, y'all.